We didn't really know how many or who was turning up today. I think our commitment to try and continue to have engagement has been there since the second ditching on October 22nd, and how we engage the workforce has been sort of our prime focus in terms of bringing this aircraft back. So I really appreciate you taking the time out of your diaries, busy schedules, to come along and kind of hear what HSSG have been working on. So why are we here? I think probably all of you know why we're here. In May and October in 2012, we had two ditchings overseas, which led to, firstly, the industry suspending flights. And when I mean the industry, it was everybody, helicopter operators, production operators, and everybody else said, until we find the root cause, we're not going to fly this again. We were very, very fortunate and aligned with our own regulator, who came at exactly the same time to put in their operational directive that said we couldn't continue flying in hostile terrain, which meant the North Sea for us. And that left us in a situation where all EC225s for us were withdrawn from service. And the commitment and how we manage that going forward. What Step Change said back in October was very clear. We would not support a return to service unless we had a definitive root cause. And workforce engagement must remain at the very heart of what we're doing. So that as we go through the process, not knowing how long it would take, workforce engagement and communication must be one of the prime commitments. And we've done a lot. We can always do more, but we've done a lot over the past nine months or so. And today is about very much bringing that into context and why we, as an industry and HSSG, believe it's safe for the aircraft to return to service. The diligence, the due diligence, and the scrutiny that we've applied, the level of alignment we've had over the past months, and ultimately what's happening next in terms of the commitment to safety for everybody else. So this will give you a chance to see on the journey that we've been, what happens next, and actually ask questions. We recognise there's concerns out there, and to ignore that would be, just absolutely pointless in our regard. But ultimately, we have spent 9-10 months working on this, and now we need to try through these sessions to instill the confidence that we have to you and understand why we feel it's okay to have made this decision. So that's what we're trying to achieve today. Nothing more than that. So we're going to give you a basic overview of the status, what's kind of happened, the investigation findings and the cause of failure, the solutions that support a return to service, where our regulators have played their part, the level of additional assurance that HSSG and others have applied, our position and the barrier model and how we're explaining it's going to work, and some forward outlook. Now, I'm not going to do this on my own. I think that would be entirely uninteresting. I think that to listen to me is not the best option. I have Alan Chesterman and Tim Glasspool. Alan works for Apache, Tim works for Bristow. They are co-chairs of the HSSG. And actually at the far end, I've got Jake Molloy, who sits on the Step Change leadership team and is also one of the key members of HSSG. So this is an aligned position. So what we have is the industry safety body, production company, helicopter company, and trade union all working together to try and help communicate this. And that's the purpose. So we're all going to speak today, and there's an opportunity to ask questions at the end of the presentation. And that's kind of where we'll be. So just to give you a rough idea of the journey we've been on, 10th of May and 22nd of October. The first incident, there was a belief that there's a crack formed as a result of a part issue on the vertical shaft. The regulator position was that we could continue to fly, and on the 22nd of October, we realised that that root cause finding was flawed, and as a result, we had to have a much greater response. HSSG came together twice that week in October and worked collaboratively to have a combined aligned position all across the airfield, all across Aberdeen. I will say that HSSG has, and I'll use this word, we've had a global impact on the position we've taken. So what's happening to us in Aberdeen and the position we are taking is impacting the rest of the world, and they're looking to us for leadership and guidance. Now, that is not our role, but it's a consequence of the alignment we've had with helicopter operators, regulators, actually Eurocopter and everybody else. So we've had a huge amount of alignment, and that has had a consequence positively for the rest of the world, I think. I'd also like to point out that, if you have questions of your helicopter operator, they are in the room today. So we have all 3 helicopter operators represented, plus Eurocopter. So from day one, we've been in the room, and we'll continue to be in the room until the end. So we had suspension of flights in the UK and Norway and other parts of the world. So it's been a long process, 9 months or so, of very detailed investigation, and we'll tell you a little bit more about that. HSSG engaged some additional independent counsel as to why to give the level of assurance that we need. But we're at the point where EASA and CEA have given us the technical requirements in terms of safe return to service. And now it's about engagement. This is a really busy slide, and it's very difficult. This is not linear by any stretch. So when we see today and first EC225 return to service, that could be 1 week, 1 day, 1 month, or longer. It's a very much a phased, periodic reintroduction as and when it's ready to go. So there is no ceremonial big lift going to happen at Aberdeen Airport. It's not going to be like the Red Arrows. This will come back as and when we do the logistics, the retraining, etc. So that's kind of the background. It's been 9 months of really aligned, joined-up thinking. Unprecedented in terms of industry response, but entirely appropriate to 2 ditchings in 6 months. So whilst this is, not normal business, it has become normal business for much of us. Alan, Tim, Jake, and myself, I think, speak almost daily about how we're managing this, as we do with all the other helicopter operators, and this process. There's been a huge amount of alignment and commitment to doing things right, not time-driven, not money-driven, but entirely right based on a gate management process and project management process. So we don't go to the next stage of the process until all the questions and assurances have been resolved at the earlier stage. So standard project management stuff for industry, so there has been no time pressure. So when we see dates like we'll return to service in May or June or July, that has never been a pressure that HSSG or anybody else has felt. It has always been about we'll go when we're ready and not before. So that's the other thing is that cost has never been a driver. At no point has anybody mentioned cost or production being a particular concern in this. Safety's been the only concern for HSSG. It's the only thing we're interested in. We're entirely independent and have no commercial model in this. And I think it's really important to understand that when you don't have to worry about cost and you don't have to worry about time, you can actually do things properly, in a proper, joined-up manner, and make sure everybody at the table has the same level of understanding before we go to the next stage. And that has been a real benefit of this collaborative working. So I'm going to hand you over to Alan just to give you a quick update. You can do it there if you want, Alan, or you come over there, just to get an update as to where we've been and what we're doing.
Good morning, everyone. My name's Alan Chesterman. I work for Apache North Sea. I'm the co-chair of the Helicopter Safety Steering Group. And at one time I was a field manager for 40s, so I can relate to the way everybody feels about using the helicopters and a helicopter that's had a flaw. So the first thing I want to say is that, so I'm just going to go through a brief summary and then I'll hand over to Tim who will go in detail through the investigation and the findings and the solution. So the first thing is that Eurocopter has thoroughly investigated the shaft failures. And as the previous slide showed, that process took a long time. And that was necessary because, we're off to a false start, if you will, with the first incident, thought got to the bottom of the problem, then another one happens and it was slightly different. So kind of back to the drawing board and figure out what's really going on. So I want to try and get across to you a sense of the thoroughness with which this was actually done over many months. So there really is a lot of understanding been developed about what happened, what the causes are. And because that was a long process and everybody's got a clamour for wanting to know what's going on, and you haven't got to all the answers yet and it's complicated, and Tim will go into this, it means that, right, we don't know exactly what the causes are to start with, so you come up with things like probable cause and so on, which can make folks feel, well, they don't really know what's going on. And that's a consequence of that big, long, drawn-out time. So, I just want to get across to you that this was done in incredible depth and detail to really get to the bottom of it. And then the mechanism of the failures was actually replicated. Okay, so you've got, this is the cause, then you demonstrate, you replicate what happened. So actually, we'll come on to it, what the causes are. It's the combination of corrosion and stress, fatigue, and that was replicated on the test bench, and then a shaft was put up in the aircraft, and the failure mechanism leading to the shaft unzipping was demonstrated. So there is a very high level of confidence that this is what the causes actually are. To add confidence to that, the investigation was independently verified, including a review by a world expert in strength of materials and fracture mechanics. He went to the same university that I went to in Manchester. He's a renowned guy. He came in and he looked over it. He visited the factory and stood behind, what the investigation had found. So we're not just relying on Eurocopter for this. Independently, there's the AAIB, which is the Air Accidents Investigation Branch in the UK. Their investigation continues. They've issued a couple of updates. They take their time, and interim report is expected. I heard it was going to be middle of July, but obviously we missed that date, so we expect an update soon. They will take as long as it takes. So the safety proposals were endorsed by the EASA, which is the European governing body for the aircraft, basically flying certificate of fitness. And so that's the European regulator. So they've gone through all of the proposals we're going to talk about in a minute with a fine-tooth comb. And over and above that, the CAA, the Civil Aviation Authority, which is the authority that governs the flying of commercial aircraft in the UK, has also gone through the findings and has accepted the recommendations, and subject to them all being implemented in the aircraft, has lifted the ban on flying over what they call hostile terrain, so flying over North Sea, where if the aircraft were to go into the water, there'd be poor chance of, difficult to recover. So the regulators are behind this. Now, there are two solutions, an interim or an immediate solution, which is to fly with the existing shafts, and a long-term solution, which is a redesign of the shaft. Now, with the existing shaft, there are a number of different safety barriers and additional checks that will be carried out and changes made that allow the aircraft to fly safely with the existing shaft. And we are convinced that it is safe to do that on the basis of the investigations that have been done and the independent verification and the approval of the regulators. The long-term solution is to redesign the shaft, because using the existing shaft imposes additional actions that you wouldn't want to do for indefinitely. So it imposes additional maintenance and so on and so forth. So the long-term solution is a redesigned shaft, but the existing shaft is perfectly safe to fly this aircraft, HSSG believes, with these additional safety barriers, and we'll be coming on to that, how they work together shortly. Am I going the wrong way here, Les? No. Nope. Okay, so next piece, absolutely critical now, and our focus now on why everybody's here today is to really tell the story of what's happened, because not everybody's on the same page and has seen what has happened and understands what's been going on. So this is a really, really important thing. Understandably, confidence in flying these aircraft has taken a big dent. And so we need to get our confidence across to you. So the focus is now on exactly that. How come it's safe to put this aircraft back into service? In terms of the interim or immediate safety measures to resume flying with existing shafts, the modifications to do those, to be able to do that and to retrain the pilots in this aircraft. I haven't used it since October last year and so on. They're all being implemented now. And the timelines of those are different though, depending on the situation, whether or not people immediately need the aircraft, what their customer, what the operator's customers are looking for. But the first aircraft may come into service in the next couple of weeks. So collectively now, our task, and industry's task, is to communicate what's been going on. So there's a big exercise here over the coming weeks and months in communicating, so that people aren't going to go offshore and go on one of these helicopters without having a good understanding of what's been done and having confidence restored in the aircraft. So that's really why we're here today. So with that, I'm going to hand over now to Tim Glasspool, my co-chair from Bristow, who's going to talk about the investigation and the solutions.
Good morning, everybody. As Alan said, I'm Tim Glasspool. I'm Head of Flight Operations with Bristow Helicopters. I'm a 225 pilot. I'm not current at the moment because the aircraft has been grounded, but I'm booked in for training shortly, so I'm looking forward to going flying it again. So I'm just going to take you through some of the main points of the investigation, root causes, and the beginnings of what the barriers are we're putting in place to make the aircraft safe to fly, and then that's going to be carried on with Les later on. So I think, has this got a laser pointer on it?
Oh, sorry, Tim.
Oh no, here it is, got it. So first of all, just to talk about the main gearbox, that's a nice coloured representation of it. Obviously they don't look like that in real life, they're pretty much grey and black. But this is the power in from the engines comes in from this side. This is the main bevel gear which drives the drive shaft up to the rotors, which are up here. And the power really comes through here, through the bevel gear and up. The weld, which is here, is to hold this bottom part of this bevel shaft on, which drives nothing but the two oil lubrication pumps. Now, one of the reasons that both the oil lubrication pumps are inside the gearbox and both on the same drive shaft is a regulatory requirement that all of the oil system needs to be contained within the gearbox, or as much as possible. So that's why they're both in the same place. It's a regulatory requirement. So that's really where the power goes, it's up. And this is really just driving two relatively small pumps. This is the weld. The reason there's a weld is you can't actually manufacture the piece in one whole unit. You can't actually machine the bevel gear with this piece in the way, so it has to be welded, and this type of weld is in pretty much every gearbox on every helicopter. So that's why there's a weld, and this was the area that failed around here. The main point about the power going through and up is the fact that even with this bit removed, if it's cracked all the way around and fallen off, it doesn't actually affect drive to the rotors. So there's not an immediate issue other than the fact that the lubrication pumps aren't being driven, so the oil flow around the gearbox stops. But of course there's still a lot of oil on all the gears, which is why it continues running quite happily for a while. The emergency lubrication system, which was fired because the crew's got an indication that the pressure had dropped to zero, fires in at the top and at the bottom, but it's mostly at the top, and that's what kept the gears lubricated and allowed the aircraft to safely ditch onto the water under full power. So this is the area where it cracked, or where they both cracked. The cause of the failure is a combination of things, which I'll come back to on a later slide, but they are essentially, well, they are the same root cause, just a slightly different initiating factor. After the cracks formed, they grow all the way around until the shaft fails after about 20 flying hours. So there's quite a lot of opportunity to catch it if you're looking for it. And of course now we're looking for it very hard. The point about this is that, again, it's on another slide, but it spins very, very quickly. So the forces involved are pretty high. I think that's that one. So really, just to take through beginnings of the investigation, it was an extremely thorough and exhaustive investigation. As Alan pointed out, it took a long time. There was a very thorough investigation for the first ditching, and the cause for that wasn't immediately apparent. It took a lot of work to actually nail it down to moisture, which was had been put in via a small plug, which is at the end of the weld, because the welding technique that's used is electron beam welding, which is a very high strength weld, but it means that at the end of the weld, where it meets itself after 360 degrees, there's some disrupted, disturbed material, and rather than leave that as a potential weak link, it was drilled out and a plastic plug goes in because there's oil that runs inside the shaft. And that was where moisture was induced for the first crack. But again, we come back to that in slightly more detail. But because that was quite a thorough investigation, and it was a fairly obscure cause, which had never really come up anywhere before, it was felt that was the cause. And then when, so of course, the second one happened, everything was reviewed and looked at again. So it's been an incredibly long investigation. Eurocopter, in their factory in the south of France, set up this war room. You can see all the different charts and things on the wall, which we will go through before. We've had an opportunity to visit that as HSSG and see them in action. Every possible cause of failure was considered. Everything had to be looked into and either ruled out or considered as a possibility and investigated further. No single cause emerged. It's a combination of things. It's the usual Swiss cheese model. There were more than one event lined up to actually make this happen, which is why it's been so rare. Because the 225 I've been flying the 225 since 2007. So there's been a lot of flying hours on the 225, and this was the first time this happened. So it was a very rare and unusual event. And the complexity and the depth of the investigation is, again, one of the reasons why it took so long. It was an incredibly thorough investigation. I don't know if anybody wants to step in about our looks around the war room and the investigation of the visits that we had.
Just one point that, we'll come on to it. So this point about the fact that having an initiate little crack, it takes about 20 hours for that to propagate around, to grow around the length of the thing so it splits into two parts. And it's a really important point. So you can see here that the guys are looking there at one of the shafts, and under a microscope they're examining the surface of where the crack grew or propagated. And that's a really important point to understand that it is 20 hours, and so they've been measuring the rates at which it grows very carefully so that it doesn't fail immediately. It's reliably understood that it does not immediately zip, go all the way around and prompt failure. It takes time for it to grow around. So it starts like a little crack, and it grows around. And then the thoroughness, again, I mean, Jake could comment on this. I've been to this room twice, and the exhaustive nature of it, with dozens and dozens and dozens of possible things all ruled out and closed out, it certainly impressed me, and the amount of effort that they put into it, incredible.
Yeah, I would supplement that. You could tell Alan's an engineer, and he's interested in the cracks. I was more interested in the instant investigation, and I couldn't help but be impressed with what was going on there. I've seen a lot of instant investigations down the years and represented a lot of people accused of failure and everything else, but I've never seen anything on that scale. It was extremely impressive, and as Alan said, we're here to talk about building confidence, and seeing that instilled a great deal of confidence in me, because to see the depth to which they were going, I've never seen so many yellow stickers in one room. It was incredible as they chased the things all the way around the room through the different stages. Really impressive. The crack stuff, for me, is a wee bit over my head, but now that I've seen Burdekin's report, I've got a better grasp of that as well, and you'll hear more about that as we go on.
So again, just working through the root cause analysis. Initially, well, not initially, it built up into 149 possible root causes, each of which is like one of these, and then there's all the sub roots off of each of all the different branches off of that. So there's a huge amount of investigation was done. Every single one of these points had to be chased down to confirm that it either was a factor or wasn't a factor, and why it was or wasn't. So there was a massive amount of work done in all of this. And eventually it was narrowed down, and the cause of the crack initiation was found. And it's a combination of 3 factors. So you need active corrosion, which is a non-conventional corrosion. It's a new term, which requires the presence of water, of moisture, and stress and temperature. So it's those three things together for the active corrosion part of it. You also have some residual stress, which wasn't fully understood at the time, within the weld itself. The process of welding it, actually, you have some stress remaining in the part when it all cools down. And plus, the actual geometry of the part as designed had some residual stress concentrators, some hotspots in it as well. And you put any one of those things individually, the safety factors were hundreds of percent. It was never an issue. It's only when you combine all these things together that you're actually able to initiate a crack and break a shaft. So all of this methodology was challenged on lots of different levels by the airworthiness authorities in Europe and the UK, and the manufacturing area, the DGAC from France as well. Also, we had the Georgia Technical Research Institute, who were working very much on the crack propagation rates to ensure that that was something that was going to be 20 flight hours and a number we could rely on. And Shining Engineering, who really were looking at the whole investigation process and ensuring that due diligence had been done and that all of the different points had been closed out. And then to cap it all, as we mentioned, we got an independent HSSG-sponsored expert to look at the overall findings and give his opinion as well. So there was a lot of investigation, and once the results were found, there was a lot of validation of the whole thing as well. So you might think, how can you get any form of corrosion at all inside a gearbox, which is full of oil and gears all thrashing about and splashing oil all over the place? Well, the only place there isn't very much oil is in the middle of this shaft, which is hollow and open to the air at the top, which is a pressurization thing, and it could be sealed, but it would be a difficult thing to do, and there's never really been a need. It's not normally a sealed part. So this inside here is open to the atmosphere. Now, the gearbox gets pretty hot when it's in operation. They routinely run about 85, 90 degrees centigrade when they're running. And obviously, at the end of flight, they cool down. So you've got a possibility for condensation. So that's potentially where water is getting in. But it doesn't matter if there's nothing to trap it. And at the same time, there's oil being sprayed up from the bottom because there's some gear splines within the shaft to lubricate those. And what became apparent was the oil being sprayed up here wasn't man enough for the job. It wasn't actually able to keep the whole part sufficiently covered in oil to keep moisture out. And that's what allowed moisture to be trapped. As I mentioned before, this shaft rotates pretty quickly. It's not the fastest rotating part in the gearbox, but it's rotating at 2400 RPM, which means that the centrifugal loads inside the shaft are about 400 G. So there's an awful lot of force to press any moisture which is trapped outwards against the surface. And the things that allowed the moisture to be trapped are there's some slight wear on these gear splines which are in here, which creating a sort of a metal paste. There's oil in there as well. And you get this slight sludge and paste, and this was trapping the moisture within it. And then there are some slight machinings, some grooves, which were to do with the weld, which allowed that paste to be pressed up and held in place while the aircraft was in flight or the part was rotating. So this allowed water to be trapped up against the surface, or the inside surface of the shaft, for long periods of time. And that, together with latent stress in the world, which isn't in every single gearbox, it was just in a few of them, and the other stress concentrators due to the design and shape of the part at the time, allowed all these things to be added together to allow a crack to develop and then to propagate. But the key factor is, for any of this to happen, you have to have the moisture here and trapped against the part. Which brings us to the solutions. The immediate solution is fairly obviously to remove the moisture. So what's being done is the oil jet is being added to and redirected as an additional jet to ensure that all of the area down here and up to these gear splines is much more adequately or properly covered in oil. I mean, now it's going to be drenched in oil. So there's no possibility for moisture to remain. And again, that's the biggest hole in the Swiss cheese. Once that's removed, everything else isn't really particularly relevant. So there are other safety measures on top of that, but that's really the key one. And before we any kind of return to flight, the interior of all these shafts are all being cleaned. I mean, to be honest, we've not found very much contamination there. I mean, even having sludge or any of this paste inside the gear shaft is pretty unusual. It wasn't an area that was looked at very closely in the past. It was something that had been looked at every, I think it's every 500 or 600 hours as part of a more major inspection. And even when we've done that, we've not found very much sludge there. And now that we've cleaned them all, we didn't have to clean very much off. There wasn't very much on any aircraft. So there's a number of unusual events that sort of came together to allow this to happen in the first place. The longer-term solution is a redesigned shaft, which is, it's hard, you don't really see it from this picture actually, but if you see the real shaft, it looks a lot smoother. There are far fewer of these ridges and things to trap moisture when it's spinning really fast. There are additional holes, so you've got to increase thickness, so you've got a stronger part, and then you've got some more holes in it to allow greater lubrication through the oil jets that spray through these holes. So that's the longer term solution. And so in the meantime, so these are cleaned. They're cleaned on a more regular basis if we need to, and the oil jet has been redirected so that there's a lot more oil washing around inside. And because we understand the cause and we understand the importance of the moisture, that's why the existing shafts are safe with these current safety measures. So we've fixed the problem, and that's why it's perfectly safe to go flying now and not wait for this shaft, which has yet to go through the full design process, certification, flight testing, and all the other things it'll have to do before it can be fitted to the aircraft. But this is still worth having, because at the moment we are having to do these additional inspections, and that they will no longer be required with this part. So there's an engineering burden on nightly inspections, which will no longer be required once this is in place. So it's still worth having the new part, but in the meantime, we're good to go with what we've got. So like I say, the key thing is to eliminate the moisture traps to prevent this active corrosion. There's a few pictures here. This was the one that failed due to the paste and the corrosion near the crack. This had a lot of this paste on it. Again, it seems to be relatively unique as to why that aircraft had so much in it. Some areas, some aircraft have been found with small amounts. But again, it doesn't seem to be that common. But this is now all being cleaned, and these are all now sort of shiny and metallic, and that's how they look. So it's before we fly it's clean shaft and remove any paste if there is any. And the initial, the first stitching, which was caused by moisture trapped in this hole and the plastic plug, which is believed to be potentially even just sweat from the guy that actually fitted it. But because of the shape of the plastic part and the shape of the hole weren't quite the same, that was very neatly sealed in and trapped. And it had exactly the same idea in that the water was pressed against the part. And again, it's in the same part of the weld, so you had the potential for, you know, the latent stress was in that particular weld. And these things came together to allow the crack to initiate and then develop. So first of all, you eliminate the moisture traps and get rid of the the possibility of water being trapped there through paste that's already in place. Then the oil jets that spray inside, you can just see the spraying through one of the holes here, have been redesigned, and there's new parts are being fitted to allow the oil spray to be much more dynamic and also to cover a much bigger area. So this whole area is now drenched in oil, whereas before it was apparent that there were, the oil coverage wasn't that good. So it has another effect of improving the lubrication of these gear splines, which of course reduces the amount of potential paste or sludge that gets produced as well. So it's kind of a double whammy having this improved oil jet. And it also keeps the whole weld zone clean and prevents any moisture from getting in or being trapped. In addition, once we do start flying, and in fact we've done this already, all the shafts have been inspected, a very clever ultrasonic inspection system has been developed by Eurocopter. It's specifically tuned for this region of the aircraft, so it's been specifically developed purely to look for cracks in this part of the gearbox. So the shape of the tool fits into the side of the gearbox. We have to remove one or two pipes on either side. So you put a camber in one side, and then the actual tool itself fits in the other side. It's shaped and designed so that it can only really go in one place. It clamps onto the shaft, and then you rotate the shaft, and you can do a full 360 inspection of that bevel, the weld area of the shaft. So it's the frequency is tuned so that it matches the size of the part, so it's as accurate as it can possibly be. The guys are routinely in the testing phase have been able to pick up cracks as small as 2 millimeters. So it's a very accurate and relatively easy to do inspection. So it ensures early detection of very small cracks pre-flight, and the inspection regime is either every 8 flight hours if you're flying the aircraft at full power, which is what we all intend to do, or it's an 11.5 flight hours if you fly at reduced power. There's not too much benefit to that, to be honest, because you're flying the aircraft more slowly, so you actually end up doing virtually the same number of flights, whether you fly it slowly and inspect every 11.5 hours, or if you fly it at normal speeds and inspect every 8 hours. So they're effectively the same thing. This will be carried out, 8 flight hours is effectively daily, so these will be going on, the aircraft will be inspected pretty much every night, unless they've not done any flying. These analyzers, they record what's been done, so you can, the data that's been collected can be emailed to Eurocopter, or even any remote sites around the world can get cross-check and verification of anything that's been seen. And we have to keep complete records of all the aircraft and all the checks. Another barrier which has been put in place is for the flight crew, which is assuming, this thing is so good, and the inspection period is 8 hours because the propagation is 20. So you're going to have to miss 2 inspections for a crack to actually get big enough to fail in flight. So there's at least 2 chances for the inspection crews to find a crack. And given that they can potentially spot them at 2 millimeters, they can definitely catch them at 5 millimeters, and anything bigger than that just stands out as a massive, great spike on here, and it's actually pretty hard to miss. We're not expecting any shaft to crack because we understand the issues, and we're removing the moisture. If one does crack, we're going to catch it on the ground with the inspections. But a further barrier, which we don't really need but is in place on top, is an in-flight system for the crews. Now this relies on the HUM system, the Health and Usage Monitoring System, which is a series of accelerometers around the aircraft, looking at the vibration properties of various different parts. And there's one channel which is it's called Mod 45, because the bevel gear has actually got 45 teeth on it, so that's the channel that we're really looking at. And the vibration spectrum of that changes once the crack has got to about 40% of the way round. So at that point, and to put it in perspective, the shafts actually fail when the crack gets 90% of the way round. So there's still a lot of time when the in-flight HUM system will pick it up before the shaft would actually break. And what we get is there's dedicated warning lights fitted to the flight console in front of each pilot. You can see they're quite prominent, right in your eye line, which will make you look down to this panel, which is the HUMS panel, and on there we get the various different warnings. There's various different things that can happen because the system itself can fail. We can get no data from that particular part of HUMS, which again will be alerted to the pilots, or if there's actually a crack detected, we'll get this Mod 45 exceed. So the vibration, if this was a graph, the vibration will slowly increase. The red line where it triggers is right down here, and the point where it fails is right up here. So the trigger point is it's very low. So if that trigger point gets exceeded, because this part's starting to vibrate now more than it should be, brings on the lights, the crews will see what they've got, and at that point, we've got 2 hours to land. Now, we've actually got nearly 4 flight hours before you would expect the part to fail. But with the usual aviation margins of safety, we're not allowing 4 flight hours, it's 2 flight hours. And in addition, the crew will be reducing power. So you reduce power to reduce the stress through this now cracked part, and you must land within 2 hours. So there's no ditching, there's no emergency as such. You've got 2 hours to fly back to a maintenance base, and there's not many places, to be honest, that aren't within 2 hours of either Aberdeen or Sunbury or Scatster. And one of the things we're looking at is that we won't be flying to those places that are. So we can rely on the fact that the crew will be able to fly back to a maintenance base. And that's it. So it's not if it does happen, if all of these other barriers have failed, for whatever reason, it's incredibly unlikely. And you actually get to this point, even at this point, the aircraft will be recovered back to a maintenance base safely, and then will be inspected to see if it's a real alarm or a false alarm. Oh, and that's now to Les for his Swiss cheese model. Thank you.
So I'm not entirely sure why this is my Swiss cheese model, but I think there's been an awful lot of technical data, and sometimes, and I'm a bit like Jake, I like things nice and simple. I like to be able to understand it, and I actually also want to be able to tell you what's different this time, because that's actually the question, why is it safe to fly now in sort of August 2013? Because it was safe to fly in May 2012. What's the difference? So the Swiss cheese model will hopefully help us do that. If you go back to what happened in 2012, we had one new barrier in effect, and that barrier was to monitor the shafts that were part of a batch number, so 10 parts around the world, at an increased frequency. Download HUMS at an increased frequency for a particular set of batch numbers. And on October 22nd, we had a ditching where there was no affected part number. And that was why there was a difference. So there was no deviation from what was required. It was a different, it was the lack of understanding of the problem that led to the second issue, not the fact that anybody was doing anything wrong. So there was one barrier added in May as a result of the ditching in May, and that was the increased monitoring. And increased monitoring is not the best barrier. It's a good barrier, but it's not the best. And it's also too far down the line in terms of, a bow tie model, because something has actually happened at that point, and therefore you're mitigating risk. So from a risk perspective, it's the best thing to do is stop it happening in the first place. So if you look at this, so in the event of a gearbox shaft rupture, we lost drive to the oil pumps, it's land immediately, boom. So that's kind of where we are. So when you look at the barriers, the first barrier that we've got now is a maintenance barrier, and Tim explained that. So that's somebody doing an intervention, cleaning the inside of the shaft, and removing any residue or paste. That prevents the crack. So that stops a crack forming in the first place. Good, solid barrier. Stop it forming, you don't have to worry about the other things. That's done every 400 hours or every 2 years, depending on flight hours, or every 2 years, whatever comes first. And maybe done more frequently, depending on how each operator runs their maintenance programs. But the minimum standard will prevent a crack forming. Good barrier. So we want to prevent it forming again. So in the event that, we don't get it right first time, we all know the Swiss cheese model, that's why we're using it. Multiple barriers are better than one barrier. We need to prevent it at a second layer. And that's this replacement of the oil jet. So that improved lubrication, that engineering modification. So that's a change in design of a part and a retrofit part. So we've got a maintenance barrier, then an engineering barrier. So that barrier will then lubricate the internals, stop the residue forming, improve lubrication, stop the crack preventing. So that's 2 prevention barriers. Great. We're really trustworthy people, so we want additional monitoring. So in the event that the first 2 fail, which is almost entirely unlikely, we need early crack detection, and that's what Tim talked about in terms of the non-destructive inspection, the ultrasonics. And that will detect that very, very small 2 to 5 millimeter crack. Much more realistic and better for everybody to detect a crack if it's formed, not likely, but if it's formed on the ground. You don't want to find it in the air. If you find it on the ground, we don't return to service. That aircraft, just because there's another 20 hours, doesn't mean this thing's going to take off. And so it will be removed from service immediately at that point. So there's no lots and lots, we've got another barrier, so let's not worry about it. Let's do an operational risk assessment and keep going. No, it's grounded and impounded at that point, and it will be resolved and fixed. And the final barrier, of course, is the in-flight monitoring. Now, I think, so the in-flight monitoring is a really interesting thing, because in November we had a safety rep meeting, and a safety rep who, actually I think is in this room, stood up and said, wouldn't it be nice if we could have in-flight monitoring in the 225? And Eurocopter, I think, if I remember rightly, said that's not possible, because it only happens in Airbus 380s, and it's a new, it's a very new feature and everything else. So I'm not going to suggest for 1 minute that this is a result of a safety rep, challenging Eurocopter. But as a result of engagement, we've got in-flight monitoring of this vibration sensor. And I think it's really, really important that that's been put in. So it gives us that additional barrier. That benefit of engagement, that benefit of challenge, and that benefit of working in this way has helped us have 4 very strong barriers. So the last barrier is monitoring. But it's an entirely different monitoring solution from we had in May 2012. So this is what's different. 4 barriers, not just 1. And the 4th barrier has been increased, it's made more robust, and it's much more solid. So that's why we have confidence that all these 4 barriers working together are as good, at least as good, as a new shaft. And that's a really, really important thing for us. So we have to have these things working in that way. The reason we do Swiss cheese is because we all understand it in our world. So we can give you the 6-page technical briefing, and you can go back and you can read that. But actually, I'm a simple instrument tech. I understand this. And that's my background. So this is much easier for me. So if you look at that, 2 prevention, 2 detection. Stop it happening in the first place. You don't have to worry about detecting it. If for whatever reason barriers fail, then we detect it early. If we miss that detection and we have 2 opportunities, we detect it in flight and land safely. So there's no requirement to ditch. It's fundamentally important that that's kind of the basis on which we're making the decision. Multiple barriers, multiple layers of assurance. And so Tim's going to do this, but I think it's important to understand that, if you look at what we've done in HSSG before, we have had to do things differently this time because we know that May wasn't good enough in that regard from an industry perspective. And what we've done differently is not this page, and Tim can talk about this. Now, this is our standard regulatory process and what each of them do. Alan and Jake will talk about what they've done, what we've done in addition to next. So, Tim, can you just run through kind of how the regulatory regime works? Because it's quite different from our normal health and safety regulator.
Yeah, it's very different because it's mostly run from Europe. So the European Aviation Safety Agency is responsible for the airworthiness of all aircraft that fly within Europe. So they are actually the authority which has the power, the responsibility for certifying new aircraft and for modifications to current aircraft. So when Eurocopter approached EASA with all of these proposed modifications, they were the ones that had the task of ensuring that they were all fit for purpose, did the job that they were supposed to do before they actually certified them and published the airworthiness directives. So it's linked with the European Commission, and it is a governmental body, but it is separate from the rest of the EU. It's actually based in Cologne in Germany. So they are the ones initially with their airworthiness experts because they do this. I mean, Airbus is a major manufacturer of fixed wing. You've got Eurocopter and Augusta-Westland, major manufacturers of helicopters. So there's an awful lot of certification that they have to do. So they are. It's nothing new for them. It's something they're used to doing, and they do a thorough job. So it was a very thorough job. You may remember there were lots of promised dates for parts and things, and the delay in every case was the fact that the European regulators had asked a few more questions, and they wanted a bit more work done, a bit more validation. So when it got to the point where they were happy with the whole process and all the modifications, that's when they published their airworthiness directive. So that was on the 16th of July. It detailed all of the modifications that were required to allow return to service of the 225. Now, within the UK, we have the Civil Aviation Authority, and they, until October next year at least, they have responsibility for flight operations. So they have limited responsibility for airworthiness. They have none for the EC225 because it's not manufactured in the UK. So airworthiness is covered by EASA, but the operations of the aircraft and how we fly it is the CAA. And that's why they produced an operational directive originally, which prevented the flight of the 225 over hostile terrain last year. And based on the EASA airworthiness directive, they withdrew that operational directive and replaced it with a new one, which allows the 225 to fly over hostile terrain, provided all of these modifications and the changes to the maintenance schedule have been enacted. So if you follow all the details in the airworthiness directive, which relates them back to a series of quite complex service bulletins from Eurocopter, the manufacturer, which is effectively the work cards and the task cards as to how to carry out all the maintenance and how to fit the new parts and all the detail work. Once all that's been done and the procedures are followed, then we're okay to fly. Well, the CAA has approved the 225 to fly anywhere, including hostile terrain. So that's where we are now. So the regulatory authorities have given their approval pending modification of the aircraft.
Alan.
Okay, so in addition to that, we had some independent verification of what was done here. So this outfit called Shining Engineering. So just to explain what they did, they were actually contracted by Eurocopter, but they're advisors on investigations, root cause investigations. They're experts in investigations and investigation process. So they were contracted by Eurocopter, but they did an independent review of the root cause analysis. They advised on it, and they ensured that everything was done properly and closed out. So there were 149 possible branches. Shining would be there saying, right, have you eliminated number 149? You know, I mean, at one time it was thought there was a different cause of what was going on in these gearboxes. Those all had to be ruled out and closed out properly. So that's what Shining did. Then the second point, and yeah, I'm an engineer, I'm not quite so like Les into the Swiss cheeses. Just this really important point about the mechanism of how a crack starts and then causes a failure. So experts in the field are a world-renowned body, Georgia Tech Research Institute. So they were brought in and they validated this whole crack propagation thing. So let's just put it into a simple, thing. You get a crack in any sort of structure, and it starts as a little thing, and then it grows. So the part doesn't fail immediately. The crack grows through it. So this was really critical to understanding. If you've got 20, does this thing reliably? Do you know it's going to take 20 flight hours? Because if you get a little crack and it fails instantly, then you've got no drive. So this was really a critical point. And so Georgia Research, that's why they were brought in to understand that and reliably know that you have 20 hours and how much time you've got remaining before your part actually breaks into 2 bits. So it's really, really important. And then finally, Professor Burdekin went to UMIST like myself, international expert in the strength of materials. I'm going to invite Jake to say a little bit about the professor, but he basically was brought in to take a look and ensure that the findings were valid.
Thanks, Alan. Burdekin was like an extra layer, which, let's be honest about it, some people in the HSSG weren't too happy about it initially. We've got 2 renowned world experts, Shane and Georgia Tech. Why do we need a third one? The third one was essentially for, like me, John Taylor, the Balpa rep, Les, and a few others, who, after May, and having had all these assurances from all these regulatory bodies and everyone else, we're still doubtful. We wanted that additional layer of assurance so that we could come to you and say, these are the experts, and we got this extra layer just to reassure ourselves. On top of that, Burdekin was able to break it down into edible chunks, understandable language, I think, far better than Georgia Tech, Shannon, or indeed the regulators were able to do it. I mean, try and read the regulatory report. It's a minefield. 3 or 4 readings and I still don't understand it. But Burdekin and that Swiss cheese model brought it down to a level that the layman here and a few others in the room were able to grasp. So it was to give us, as a group, that degree of assurance that allows us to sit here today and talk about what's been done. That was why Burdekin was brought in.
So I'll just kind of recap on a bit of a summary. So what's different? I think what's different is that we've got 3 layers of independent verification over and above the regulatory process that happened in May. So 3 additional layers of assurance in terms of the process that we've gone through. We've got 4 additional safety barriers and a long-term solution. So not just 1 safety barrier, but 4 applicable, valid, assured safety barriers that have been checked not only by the regulator, but by the 3 independent experts. So you've got layer upon layer of assurance and layer upon layer of a barrier. And that's quite different when you look at where we were in May last year. And we've needed that. We also needed the likes of Burdekin to help us ask the difficult question. Our job is oil and gas safety. To and from work in a helicopter is part of that. But not one of us, well, apart from the helicopter operators and HSSG, have the competence from an engineering perspective to ask those difficult questions. So we had to pull in the necessary technical expert to give us that assurance. And we went away and did that, because that's the only way we can stand in front of you to say, what else have we done? So that was why we did it. And I think when you look at the 4 barriers, there's a really important 5th barrier that doesn't, show in the Swiss cheese model, and that's the pilots. We have, without any shadow of a doubt, highly professional, competent helicopter operators. But we've got pilots that under no circumstances are going to get in these aircraft if they believe they're putting themselves or their family at risk. And that's the most important barrier. They're not going to ask you to get in the back if they're not prepared to get in the front. And all the engineering and the good work we've done has to work for the pilots as well. They're flying much, much more frequently than I will and you will. And their safety is equally as important.